Dear students, welcome back to another presentation on micropumps. So in our last class, we had discussed on microfluidic systems as well as the micropumps. In today's class, I am again going to highlight about different types of micropumps. The references that I am using here in this presentation includes the reference text as well as a few research papers. Now these research papers are purely used to explain the concepts regarding the different micropumps. Before going into the different types of micropumps, let me start with the two different main groups of micropumps. So micropumps can be grouped into mechanical and non-mechanical devices. We have already understood a few mechanical micropumps. Now the basic concept underlying a mechanical micropump is that it contains moving parts, which are mainly actuation and microvalve membranes or flaps. The driving force can be generated by using several types of micro actuation mechanics. That is, they may be mechanisms including piezoelectric mechanism, electrostatic actuation, thermopneumatic, pneumatic, magnetic effects, electromagnetic, bimetallic, ion conductive polymer films, phase change and shape memory alloys. Now the biggest drawback of external actuators is that their large size, which restricts the size of the whole micropumps. But however, that plays as an advantage, that is, this is relatively large force and displacement generated by external actuators. Now the non-mechanical micropumps. The non-mechanical micropumps have no moving mechanical part. They need a type of mechanism that can convert non-mechanical energy into kinetic momentum. In general, non-mechanical pumps do not need physical actuation components. That is, the geometry, design and the fabrication of these micropumps are relatively simple and easy. These micropumps, however, have certain limitations, such as the use of only low conductivity fluids will result into an actuation mechanism which may interfere with the pumping liquids. Non-mechanical micropumps can function with a variety of mechanisms. The mechanisms that we are going to discuss in today's class include electrohydrodynamic, electroosmotic, electrochemical or ultrasonic flow generation, just a few of the actuation mechanisms that are currently studied. So in a nutshell, I can classify the micropumps into mechanical and non-mechanical, as you can see in this slide. So you may have the electrostatic micropump, which uses vibrating diaphragm. You may have the piezoelectric ones, which uses vibrating diaphragm, peristaltic movement, flexural plate waves. That is the one which we discussed in our last class. There may be thermopneumatic. There may be shape memory alloy, then you may have bimetallic, ion conductive polymer film and so on. And on the non-mechanical side, you may have magnetohydrodynamic, electrohydrodynamic, electroosmotic, electrowetting, bubble type and electrochemical type. Well, as we have already discussed about electrostatic micropumps, wherein the use of electrostatic forces, these uses the electrostatic forces in their actuation mechanism. That is, the pressure difference induced by the membrane deflection in the pump chamber forces fluid in the reservoir to flow in the microchannels. So that was regarding electrostatic micropumps. Then we also dealt with the piezoelectric micropumps, which is based on the principle of the piezoelectric actuation. Now let me introduce a third type of mechanical micropump, which is based on bimetallic type of micropumps or bimetallic actuation. Now, we have already dealt with bimetallic sensors, where we know that a bimetallic sensor is actually constructed with the help of two different metals in fact, joined together, and their thermal coefficient of expansions are different. The deflection of a diaphragm made of bimetallic materials is induced against a thermal alternation as long as the two chosen materials possess adequately discriminative thermal expansion factors. That is, the two metals that are joined have different thermal expansion coefficients. So here is the picture of one such bimetallic micropump, where you can see that there is an inlet and there is an outlet, and this is the pumping chamber, and this is supported by a bimetallic actuator which can be heated externally. So as and when you are going to heat the bimetallic actuator, that will see that there is a temperature difference between the two metallic parts that has been joined in a bimetallic actuator, as a result of which there will be a deflection of the diaphragm. So what happens is this will induce thermal stress because the coefficients of the metals differ, providing a means for actuation. The implementation extremely simple and large forces generated, but the deflection of a diaphragm is only that can be achieved by thermal alternation. So the same theory behind the bimetallic sensor is applicable here in the bimetallic micropump, and hence micropumping can be achieved. Now one example of a bimetallic thermal actuation and thermal pneumatic actuation mechanism, it can be had with the help of a bimetallic actuator made of aluminum silicon membrane, which when heated the membrane deforms in a downward direction. At the same time, the gas in the air chamber expands due to the heat to support the bimetallic actuation, and with the result that a flow rate of 336 microliter per minute can be achieved when the open pressure was about 0.5 kilopascals. Let us see what are the merits and demerits of a bimetallic micropump. The forces generated through bimetallic actuation are large, and the implementation is simple, as I have already suggested. And then thermal expansion coefficients of materials that are involved in bimetallic micropumps are small. Hence, the least of the deflections are achieved in bimetallic actuation mechanism, which means that even the smallest deflection can be observed and measured. Bimetallic micropumps require low voltage values as compared to other micropumps. But the drawback of bimetallic micropumps is that they are not suitable to work at high frequencies. Let us now move on to another type of mechanical micropump, which is called as the ion conducting polymer film micropumps. Now these are in short called as ICPF. Now an ion conductive polymer film micropumps are polymer MEMS actuators that can be actuated in aqueous environments with large deflection. They need very low power input than the conventional MEMS actuators. So that is the greatest advantage ICPF has on the other types of micropumps. Now what is the construction? Now here a core layer of ICPF PF is made of a sort of perfluorosulfonic acid polymer. So that is the central core layer, and this is actually looks like a sandwich diaphragm between two thin films of chemically plated platinum. So two thin layers of platinum are actually supported by the core layer. And then these two films have high electrical conductivity. One end of the diaphragm is fixed, and the ICPF diaphragm can be controlled by bending in the direction of either upside or downside as long as the appropriate pair of voltages is applied at the electrodes. Now let us see what happens when such an application of voltage is done across such a ion conductive polymer film. Let us see the diagram. Now this is the picture of an ICPF micropump, or at least this is the core layer. Now ICPF actuator is commonly called as an artificial muscle because of the large bending displacement, low actuation voltage and biocompatibility. Now you can just observe the presence of an electric field causes the ions in both the electrodes, both the sides of the polymer molecule chain, to move to the cathode. Now when you are applying an electric field, the ion with a positive charge will take some water molecules and move towards the cathode. Now this particular micropump is actually used in aqueous environments, as I've told you in the very beginning. So when an electric field is applied, all the positive ions will start moving towards the cathode along with water molecules. So this movement, this ionic movement, causes the cathode to expand and the anode to shrink. Now the presence of an alternating voltage signal will bend the films alternatively. So this is what we observe in the second film. So here you have the material where the ions are spread, but when you apply an electric field, you find that the cathode is having more ionic activity attracted towards it along with few water molecules, as a result of which they are expanding largely while the anode is shrinking. So as a result of which, what happens is there is a bending of the material either to the upper side or to the lower side. So what happens is there is a stress gradient built from the ionic movement due to the electric field, and now this stress gradient will act as the actuation, as a result of which microfluids gets pumped. So this is how ICPF type of mechanical micropump is going to work. Now this is a slide which gives you the details of how the construction of ICPF is made. Let us now look into the example of an ICPF type of micropump. Now a microcatheter was developed with active guide wire that had 2 bending degrees of freedom. Similarly, a multi-degree freedom micromotion device was also constructed. An underwater fish-like micro-robot using ICPF actuator as servo actuator swimming motion with 3 degrees of freedom is another example. So that is about the mechanical micropumps. Now let us move on to non-mechanical micropumps. Now this type of pump has to transform specific non-mechanical energy, as shown in the bracket. These are the mechanisms which we are going to discuss in today's presentation. So they include electro-osmotic, electro-hydrodynamic, then electro-wetting, etc. So they are the mechanisms that are studied. So what happens in a non-mechanical micropump is that non-mechanical energy is converted into a kinetic momentum so as to drive fluid sample into the microchannels. So non-mechanical micropumps can be further categorized as being electrical, chemical or magnetic. Electro and magnetokinetic micropumps convert electrical and magnetic energy into fluid motion. The pumping is continuous, so the resulting flow is generally constant and steady. Now let us look into how is this electrokinetic or the kinetic momentum is developed. Now in an electrokinetic micropumps, an electric field is used to pull the ions into the pumping channel. So this is what happens when you apply an electric field. They are used to pull ions into the pumping channel, in turn dragging along the bulk fluid by momentum transfer due to viscosity. So a few ions are actually pulled up with the help of the electric field, which results in the dragging of bulk fluid by momentum, which is due to viscosity. So this is what results in non-mechanical micropumps actuations. This type of pump has to transform, well, this has been already told. Let us now look into the different types of non-mechanical micropump. So first of all, we have the electrodynamic micropump. So before going into the hydrodynamic pump, let us look into a certain part of science which is actually contributing to the activity of a non-mechanical micropump. So let me look into the electrochemistry, which is actually study of chemical reactions caused by the passage of electric current, which is a very important contributor to the microsystem design and fabrication. Now, electrochemical reactions are used in many engineering processes. Now, principal application of electrochemistry in microfabrication and microsystem design are basically two. We have already heard of Liza process, wherein the electroplating of polymer molds and thin metal layers by electrolysis is based on electrochemistry. Now, the second important aspect that also deals with electrochemistry is the electrohydrodynamic pumping, which includes two mechanisms. One is called as the electrophoresis pumping and the other is called as the electroosmosis pumping. Now let us see how electrohydrodynamics is going to influence the micropumping activity in a non-mechanical micropump. Now in a EHD micropump, the force is generated by the interaction of electric field and mobile charges in the fluid. These pumps have emitter and collector electrodes that are regularly spaced along a microchannel and require no moving parts such as impellers, bellows or valves. The electrical charges thus generated from the electrons mobilize according to the direction of the electric field that is built up by the electrodes and track in the surrounding liquid molecules to move together by the ion dragging force. Now here is the diagram which shows a simple electrohydrodynamic micropump. So you can see that there is an emitter electrode, there is a collector electrode. They are placed in such a way that they are interspaced between them. You have an inlet valve and an outlet valve. So the mechanism involved, as I've suggested already, is by the interaction of electric field and the mobile charges in the fluid. Okay, so let us see a few examples of electrohydrodynamic pumping. Now the first DC charged injection EHD micropump comprised of two electrically isolated grids. The flow rate thus realized was about 15,000 microliters per minute, and the pressure head of 1.72 kilopascals were achieved at an applied voltage of 800 volts. Another EHD micropump based on travelling wave induced electroconvection had flow rates of 0.05 to 5 microliters per minute was in fact achieved. Now, as I was telling you about electrohydrodynamics, which deals with the motion of fluids driven by electric field applied to the fluids, there are actually two principal applications of EHD in microsystems. The first among them is the electro-osmotic pumping, and the second one is the electrophoretic pumping. These unique pumping techniques are used to move chemical and biological fluids in channels with extremely small cross sections ranging from square micrometers to square millimeters at flow rates in the order of cubic micrometers per second. Now, microfluids are widely used in pharmaceutical industry and in biochemistry analysis using extremely small quantities in the order of few hundred nanoliters. Remember, 1 nanoliter is about 10 raised to minus 9 of a liter. Now let us look into the electro-osmotic micropumps. Now EO flow, that is electro-osmotic flow, is the motion of liquid that is induced by an applied potential across a capillary tube or microchannels. The fluid with electric conductivity feature is driven by appropriately exerting an external electric field upon the channel walls that are naturally charged. Now here is the diagrammatic representation of one such arrangement where you have the electrodes placed which are actually applied with a potential across and thereby giving inlet and outlet to such a representation. Now let us see in detail how does this electro-osmotic pumping actually takes place. So electro-osmotic pumping is used to move electrically neutral fluids through channels of extremely cross section, as you can see in this picture. Now this is the smallest cross section that is typically exaggerated so as to see what is the inside of such a micro channel. The condition is that the walls of the conduit or channel must have attached immobile charges. Now here you can see that a glass wall is shown in the figure can produce such immobile charges along the surface if it is coated with either ionizable material, for example, deprotonated silanol groups, or with strongly absorbed charged species that are present in the fluid. So you can see that from the figure you can see that so on the walls of the glass tube you can see that there are immobile ions. At the same time there are mobile cations. So as these mobile cations move, there is a drag effect here, as a result of which the other ions are also pulled or dragged into the micro channel, or rather this will ensure that there is a pumping activity taking place. So what is it? It is the mobile cations which are moving, and they as they are moving will have a drag effect on the other ions as though they are pulling the material through the microchannel. Now this is how electro-osmotic pumping is actually realized. Let us now look into a micropump, EO micropump, that uses deionized water as working fluid. The maximum flow rate achieved was about 3.6 microliter per minute, and the pressure of about 2026.5 kilopascal were obtained when an applied voltage was about 2 kilovolts. Similarly, another EO micropump with high pressure was constructed wherein the flow rate was about 0.47 microliter per minute and the pressure was about 72 kilopascal when an applied voltage of 3 kilovolts was applied. Let us now look into the second type of EHD pumping, that is electrophoretic pumping. Now, this method of pumping is often used to separate minute foreign particles or species from the bulk fluid. Microfluidic systems with electrophoresis are widely used in biomedical and pharmaceutical industries. The movement of the ions of the particles in heterogeneous medium is prompted by an applied high electric field as illustrated in the figure. So the ions with different charges move in the opposite directions along the channel in the separation process. When the flow is fully developed, the ions in the streams can automatically separate themselves by their inherent electro-osmotic mobility under the influence of the applied electric field. It is highly desirable situation in chemical and biological analysis in which the separation of various minute species is often a difficult task. Now we can look the activity which has been highly exaggerated. So here you can see that foreign particles can be separated by this mechanism, wherein you can see that the positive charges are moving, positive ions are moving in one direction while the negative ions are moving in another direction by the mechanism of electrophoretic pumping. Now let us see another type of non-mechanical micropump, that is electrowetting micropump. Now, electrowetting micropump is a microfluidic phenomenon that is currently used as a driving mechanism for fluidic devices. Electrowetting involves modifying the natural surface tension or capillary forces intrinsic to an oil and water interference at small length scales. So, at less than 1 millimeter distance, the electrical and surface tension forces are much stronger than gravity. Let us have arrangement. The digital electrowetting is applied to control the surface tension between the solid electrode and the liquid phase droplet. Now here is an arrangement for one such micropump. So, in electrowetting, the applied voltage to the dielectric layer decreases the interfacial energy of the solid and liquid surfaces, causing fluid flow. Heating of the liquid is not at all required. Response is faster and power consumption is lower, both as compared with thermocapillary micropumps. Liquid metals, you can see in the picture, liquid metals contacting electrolytic solutions will develop charged interfaces that will act like capacitors owing to electrochemical reaction. So this is how an electrowetting process is incorporated as a micropump, which is also an example for a non-mechanical micropump. Let us look into an example of an electrowetting micropump. For the actuation energy of micropump, the surface tension induced motion of mercury drop in a microchannel filled with electrolyte was used. The micropump consisted of a stack of 3 wafers bonded together. The flow rate of 70 microliter per minute and pressure of 0.8 kilopascals were achieved at 2.3 volts with a frequency of 25 Hz and a power consumption of 150 microwatts. So with that I conclude this particular presentation. So I hope you have been amply address with different types of micropumps, both mechanical and non-mechanical. So we have found that mechanical have moving parts, while non-mechanical have the mechanisms or the actuations converted into a kinetic momentum. Thank you.